We're going to use an EGS single phase SINEWAVE inverter control board. So for this video I'm going to be using photos of the modifications that I was doing and explaining what I actually did to this UPS. So to begin with, normally as always, this is just tip of advice and the safety precautions that you need to take, and this document I always read it out and share with you. I just want to share so that if someone has got this inverter can actually benefit. And also what I'm going to share for the inverter control, you can actually do it for any other inverter or any other project that you actually do for inverters. So the resources required, obviously there is a microcontroller that I use, the PIC 16F887, that you actually have to use as a control board, and also this soldering and wiring that you need to do. I've done a number of projects on this channel that you can actually refer to and use for the benefit of this project. And if there is any feedback that you would like to pass on to me, that's my email address. Thank you. I hope you enjoy electronics. Right. Well, these are the photos of the UPS that I actually modified. Okay, this is the big motherboard that it comes with. I didn't even go and try to repair it. I just said, okay, we take out this board and replace it with the EGS002 controller, which is this one. This is the microcontroller by Philips S87. There is a baseboard, the power board. There are cables that come to these two. Okay, and these are the cables that we are interested in because the motherboard is going away. Right, the cables are these ones. It's using a chip for driving the MOSFETs. Right, okay, the board, the power board actually uses this MOSFET driver, the SI9910, which is a single MOSFET driver, and this cable you have to identify which line is which. There is the pulse width modulation wire, the power for the supply of the ICs and the components, and then there is the temperature wire, then there is also the ground wire. So you have to identify which one are they. This is the power block. Here's the positive block. The positive, it goes on the aluminum heatsink, and then the transformer terminal is here, and then also the transformer terminal of the other side is here. These are capacitors, and here is the ground that goes on the bottom of the power block, that goes straight on the board. Right, here is the input, the 48 volts input, and here are the cables coming from the baseboard, which is the power board. The current sensor for the DC is here, and then at the bottom of the UPS, that's where the filter and the AC current sensors are, current transformers, that is. Here is the choke. This is the bottom of the motherboard. Right, okay, so what we can discuss here is, okay, this is the 12 to 15 volt supply, this part here, which also goes to there, right? 15 volt supply. This broad track here is actually the ground. Okay, so we have the ground here, the ground there, and the ground here. Here is the pulse width modulation cables. So you have the high side and the lower side here. Well, you still have to identify which one is going where. Right, here is the bottom of the wiring that I was doing. Okay, this is basically ground, and that one ground, and then the pulse width modulation must correspond to the top and the bottom, side A and side B. Make sure you actually wire it correct, following the EGS002 board. Okay, right. You have to identify which one is this, the cable that is coming here on the, this is the lower side of the H bridge, and this side is the top side of the H bridge. If you choose this side to be A and the other side B, it must also correspond here. Okay, right. And this is how I wired. So you have actually 4 wires for side A, side B, top, bottom, side A top, side A bottom, side B top, side B bottom, or if you want a high and low side. Okay, so 4 wires must go to drive the power board below them. This cable is coming from one side, which is, if you say, side A, and then this one is coming from side B, whichever way you choose, but they are coming to the EGS002 board, right? And here it is. So you have the power supply here, the 12 volts, and then you have the 4 cables, 1, 2, 3, 4, for the pulse width modulation signals to the mother, to the power board, right? The same here, and the LED was flickering there because it was already active, right? And the UPS has got a very big, heavy transformer. Here's the transformer, the black and the white. These are actually bars, metallic bars, which are wound, which are the primary winding for the transformer. Here's the filter board. The output of the transformer comes here through filter board, through capacitors, and then goes output here on the black part here. This board, I took it out, the filter board. The transformer I used for feedback is this one. So this is the cable output for the filter board. I used that feedback for sensing the output, the AC output, and also sensing the level of the AC output, and also to check whether the inverter is running properly. Okay, using the program. I'll share with you the program. Filter board, top image there, right? And the fan, you can identify the fan here. It has got 3 fans. This is the fan for the bottom module for the Max 5000. It has 2 modules. The top module, which is the control module, and the bottom module, which is actually the power module for the transformer. Well, basically it's just a transformer, right? So the top module is the one with the MOSFETs. The bottom one is one basically with a transformer and a filter board. Top has 2 fans, right? Okay, I to create a power supply for the fan. And, this is the cable for the feedback circuit that I used. Traced its wires from that small transformer using this cable back to the control circuit that I created with the PIC 16F887. Right, so I took out all this because they were not necessary. Okay, then I left these cables. These are for other control. I think it was mainly for automatic voltage regulation. Okay, so I was not using these ones. I didn't use those ones. I left them out. That's the transformer for the feedback. this is the input from the transformer, and then filter out goes output from there, and then you have the current transformers for the AC here, 1 2 3. But on my circuit they were not responding, so I just left it out. But I had a program for them, but they were, seems like they were not working for my design. Okay, so this is the filter board still, right? Filter board. This is the microcontroller board that I made for the inverter management. Okay, the inputs. Okay, the inputs were that side, and then the output for indication for the indication that side. This is the ICSP terminal for programming the microcontroller. This is how basically it was looking. This is the feedback part I used. Okay, the feedback, AC feedback for the EGS002 board. The power supply with a relay for turning on, right, controlled by the microcontroller there. And here I used this feedback circuit. Okay, and let me show you the circuit that I chose for the EGS002. I used this circuit here. Also, this is the power supply for the fans, for the 3 fans. The fans are 24 volt, and we are using 48 volts, so I had to build a power supply for the fans. Okay. This is the power supply for the EGS002, the regulators here. There's 12 volt and 5 volts, so you need to supply 12 volts and 5 volts for the EGS 002. Here I had about 15 volts that I was supplying from a power supply, a DC to DC converter that I took from another UPS. This is the DC to DC converter. Cut out the other extra parts that I didn't need. So I had an input here of 48 volts to 60 volts, and here I modified it so that I get 15 volts here. Right. Okay, and then this is the power supply for the whole control circuit. Okay, including the EGS002, the PIC microcontroller control circuit. Right. Okay, not much of it. Okay, this is the output result. Okay, the display which comes together with the EGS002. My meter was measuring 195, so I was having 100k and 5.6 here. Okay, it was measuring 195. Right, so you have to make some adjustment here. After some adjustment, it went up to 202. I finally made it to run on 221 volts. Okay, AC output. The temperature, I didn't use the temperature feedback on the EGS002. I used the microcontroller temperature sensing, so it will just cut out if there is a over temperature. Okay, and this is the output, measured output with my scope, pure sine wave output, and I was measuring on the feedback transformer. That was the output on the feedback transformer, right? And then it was exactly the same. I also connected a transformer at the output, and it was giving me plus minus that output. The operational manual. Okay, so you have 5 LEDs that show you the state. Okay, there's battery high or battery low. Just adapted this program from my previous project on a 48 volt solar inverter. Right, so that's where the solar low coming out, and then this one shows you the state of the AC voltage, and then this one is the general state of the inverter. Off, it will be flickering. If it's in solar mode, it will slow flicker. Then the temperature LED is that one. The overload LED is that one. Indication, that's plus minus the operational manual here. To switch it on, you press this button for 5 seconds. To switch it off, you have to press both. Okay, and the release, then it goes off. To change the source mode, because you can actually have the battery mode, or you can put solar straight. It runs on solar only without a battery. So you press this button for 5 seconds, and then changes the mode. Right, okay. Then well, the other parts you can just read. Right, and this is the design plus minus. Okay, the rugged design on the microcontroller, the PIX 16F887 or even the 877, you can choose. Right, this is how I designed it. The ICSP, the power supply, the inputs, sensing, the buttons input. This is the temperature. There's a thermo switch actually on the board, so it has a thermo switch. Then there's I used a thermistor on this pin here. Okay, this is the output for the indication, and here output for the relay and other the fan, running the fan after after the temperature is reached a certain point. Okay, so you have this program. Okay, battery checking, analog input. Right, this is the on-off switch. It's a negative input. You switch to put a negative. Right, and then the 5 seconds, to T on. Okay, I'll put 1 second to T on. Right, when all these conditions are met. Okay, and switch off is actually both here, negative, and then it switches off. Right, that one 100 milliseconds, and it actually goes off if when you release that. Here I'm using LDO Micro build 5411. Right, okay, so here it is, the input for the switches here, and then I've added some notes here. Okay, the battery that I used for the matrix 5000 by APC is a lithium ion battery with a maximum voltage of 54 volts. So if you calculate using this formula here, you get about 495 units. So at 495 units, the control module must say over voltage. You just want to keep it safe, because the lithium ion batteries, they do not want overcharge. So below that is okay. And actually the way this control module is mounted, they are charging up to 53 volts. The default is actually solar. When you power the module, it goes to default of solar, so you have to change for the battery manually. Right, okay, these are the testing, and this is just meter indication for the state of the supply. Right, okay, so the LEDs are having two functions, for metering and for state indication, and also fault indication. Right, okay, so two functions for the LED display. And then here are the current. What it does is it also checks the levels, and then warns the user of if like battery is getting low, and or if the current has gotten to about half, above half the rated current, it gives you a buzz. So this is the maximum power voltage tracking, sensing, right? And then also when it does that, it flickers the two LEDs, the clip and clop. Okay, these are just two LEDs flickering. They are here. These are the LEDs. So you have your clip here, and then the other is a clop, which is that one, LED number 1 and LED number 5. They will be alternating when you are actually on maximum power voltage tracking, which also checks the maximum power current. Okay, or which if it has gone above half. Okay, and then you have a temperature sensing circuit. You have a thermistor. The thermistor is actually an NTC, negative temperature coefficient thermistor, and you also have a thermo switch, which it just grounds the input. Okay, you have the same fault. Okay, the LED just indicates that there is a temperature problem, right? A DC current and AC current there. Here I've put 780 units. This is around about 85 volts, and then this is around 10 volts. If the current transformer gives you a rectified output of 10 volts, that's over current. And here also, if it gives you an output of around 85 volts rectified, you have an overload or over current DC. And then there's some delays there. I made it to 3 kilowatts. We could actually ion, use a 2 kilowatt ion. You could actually heat up and actually iron some clothes using this inverter. Right, so adjust the current rating here, so that you have the current setting. Right, AC voltage, normal, it's around below 200. Okay, anything above, that's around 21 or so volts. You have over voltage or AC voltage. This is measured on that small transformer that I was showing you. Right, I'll try to simulate. This is the simulation. I'll share with you this diagram. Right, these supplies here, they are representing the current transformers. This is the DC current transformer, and this is the AC current transformer. On that matrix 5000 that I did, the AC current transformers were not working, so this part was not basically not installed. It is there, you just measure, but nothing was coming out from the current transformers. And then here is the feedback from that small transformer, the AC feedback. I've written there, it's actually, let me just zoom so that you see what is written there. Set at 21 volts maximum, okay, output of the transformer, and 18 volts you would say AC is now below the rated AC, which is around 190 volts AC output. So you have to give an alarm there, right? And then here you have a thermo switch. This is the IC in the form of a TO220 a package. It's a 67L100P. It's a thermo switch. It just grounds the input, right? And then here you have a negative temperature coefficient. Going down there, it actually reduces in resistance. If it's getting hot, then it will start the fan, right? Okay, the other ones are pretty much obvious. The microcontroller here is actually loaded with this EGS file, which I'll share with you. Okay, right, and it's running at 10 megahertz. You can choose up to a maximum of 20 megahertz, I think, for the 887. Right, okay, so that's the EGS file running the microcontroller. And here you have relays. This is the AC output relay. It comes after some delay when the system is switched on. This is the power on relay. When you switch it on, it comes on, and then after some seconds this comes in to give an output. here's the display for the LEDs. They are actually labeled, right? The zooming is not very stable. Okay, right. But anyway, this is LED number 1, which indicates battery voltage, also the battery level when the battery is gone low or solar supply has gone low. And here AC voltage fault, if AC has gone too high or too low. Also level of the supply, which is well, that's 2/5, right? And then here the state. This is the LED that is, even if it's just off, it's always running, depending on the source that you select. When it's in solar mode, it's flickering fast. When it's in battery mode, it flickers slow. And then also that's 3/5 of the supply level. And then this indicates the temperature high, or when you have over temperature, it indicates the temperature, and that's 4/5 of also supply. This is overload, or 5/5 when the battery is full, or the battery solar supply is good enough, okay, to the max, right? So, and then okay, the input, there are two switches that I have selected. The matrix 5000 has got 3 buttons, but I have selected the first and the last buttons. Okay, the one to the right is actually the source button. The one to the left is actually the on-off. Pressing both and releasing it will actually reset, or it will actually switch off the inverter, right? Pressing this one will switch on after some seconds. Pressing this one will switch between source, the solar or the battery, right? Okay, default is actually solar. When you just power the module, it goes to solar supply. Okay, right, let's try to simulate, and let me just zoom a bit so that you see plus minus okay, a better view. Okay, let's start simulating. Right, it's now running the simulation. Right, okay, now you see, just when you switch on, it goes to solar supply default. Okay, right, you see this LED is flickering, indicating that the system is active, but it's off, right? So switching on is pressing this button for some time, and then it goes on. Okay, switching on, press, remain pressing until the LEDs start to roll up. Okay, depending on the level of the supply, the LEDs will go up like that, rolling up, down, rolling up and down, right? If there is any like a problem, like a temperature has gone down, right, the fan will start. Okay, even if the temperature normalizes, it will continue running for a minute. Okay, but if you have DC current too high, first it will pass through a point where it actually just warns you of an overcurrent. Okay, I think this is overcurrent mode, and then later on it actually switches off. This is now a fault condition. Okay, and it shows you this LED here, that's overcurrent. If right, you reset here with this one, these two together, then release, because they actually activate on the release. Okay, then you have actually reset. The buzzer will go off for some time and go on for some seconds. You can check the program, how the buzzer behaves. Okay, right, so these are the inputs to the control module. I'll share with you this one, and you can actually start simulating and building the circuit if you are interested. Right, I've used Proteus 8,10 service pack 3. So this is set at 85 volts, and anything beyond that overloads. That's why I put 90 volts here, and this is 10 volts of a current. That's why I put 15 here, so that I change here on the potentiometers rather than changing the supply, because that I do not have good simulation there where I can change the supply here from the current transformers. So I'm actually adjusting the ports so that the voltage to the peak is changing, but otherwise this is a fixed resistor. Okay, this is not a potentiometer. This is a fixed resistor, 4,7 kilo ohms, and the other one is the 100 kilo ohm. Right, only the temperature sensing potential divider here is 10 kilo ohm here, because this is 5 volts supply to the board. Okay, the VDD for the microcontroller, and the thermistor is an NTC, negative temperature coefficient, and it's 10 kilo ohm at room temperature. And when the temperature rises, this resistance goes low. That's the matrix UPS converted to an inverter, and that's the output. Battery. Here's the battery. Specifications. Battery specifications. Okay.